In this video, we present boosting object detection with zero-shot denied domain adaptation. Object detection is a crucial computer vision task. However, the models could suffer from decreasement when encountering some extreme situations, like low-light scenarios. In low-light scenarios, there are degradations due to low visibility, color distortion, and noises. The prior paradigms in low-light detection could be roughly categorized into three classes. The first one is detection by enhancement, which is to use a frozen enhancer to enhance the input images for the detector. The second is enhancement for detection. It is to train an enhancer that could improve the detector's performance on low-light images. And thirdly, we have low-light learning strategies. For example, maybe the researchers could use the well-lit images and the low-light images and align their distributions to make the model perform well on the low-light data. And for ours, our advantage is that we only use well-lit images during the whole training pipeline. Specifically, we work in a new setting called zero-shot denied domain adaptation. Different from the prior paradigms that work in fully supervised or domain-adaptive learning, we are only given well-lit images, and we aim at learning an object detector that could generalize well to the low-light data. Here, our key idea is to introduce the low-level vision's Retinex theory into the high-level object detection task. In Retinex theory, we observed that an image I can be decomposed into the reflectance map R and illumination map L. And in this theory, it illustrates that the illumination or the visibility of the image is only controlled by the illumination map, so it's illumination specific. And on the other hand, the reflectance map R is illumination invariant, which is also our target feature to learn. Our solution is that we propose dark illuminated net, shorted as DAI net, is able to learn illumination invariant representation from only well-lit training data. And here we show the training pipeline. It consists of three components during training. The first is the dark ISP that synthesizes low-light images based on the given well-lit image to create a pair of input images. And secondly, we have a pre-trained and frozen Retinex decomposition network that will decompose the paired images into pseudogram truths, the reflectance and the illumination maps for the supervision of DINet. And at last, we have the proposed component DINet. It can be established on any existing detector, and we only need to add a reflectance decoder during training. Our first contribution in DINet is to learn Retinex-based reflectance representation. First, to incorporate reflectance representation knowledge, we introduce a reflectance decoder after the detector backbone, and we use the pseudogram truth from Retinex decomposition net to supervise it so that it could learn how to predict the reflectance maps. And naturally, the reflectance knowledge is introduced into the network backbone, which will further benefit the other task detection. And secondly, we propose an illumination invariance reinforcement strategy to further enhance the illumination invariance from a feature level. It's actually termed as a mutual feature alignment loss that aims at aligning the backbone features regarding the two paired input images. Secondly, we aim at improving the vanilla image decomposition process to further enhance the reflectance representation learning. So in a vanilla image decomposition process, usually the interchangeability of reflectance map is considered. Given a paired well-lit and low-light images, when we decompose them into reflectance and illumination, we should be able to exchange their reflectance map and reconstruct the exchanged ones to the images, and they should perfectly reconstruct the original images because the reflectance map should always be the same. And here we propose our second contribution component called interchange recomposition coherence procedure, and this is shown on the right of the figure. It consists of three steps. The first one, we still interchange the reflectances of the two images and try to reconstruct the images. And secondly, we recompose the reconstructed images into the reflectances only using the reflectance decoding branch here. And at last, we require the coherence between the two rounds of decomposition results. And to do so, we propose a recomposition coherence loss to require the consistency between the first round reflectance map prediction and the second round. After introducing our method, we show the comparisons. The setting is that we train on the source dataset and directly test on the target dataset. First, we have face detection. We use Weatherface and Cocoa dataset as the source dataset respectively and test them on the Darkface dataset using DSFD and UDO V3 as the base detectors. And we can see that they both work very well and outperform the prior sorted methods. And secondly, we perform object detection on Cocoa and test on XDark using ULOV3. And following MAET, the main comparable method, we also fine-tune our model on the XDark dataset, and we also outperform it by a large margin. Recalling that our method only introduced a very small change to the architecture, a reflectance decoder, so it's very model agnostic and has high potential to generalize to other vision tasks. Here we show the results of generalizing to dark image classification. Ours is the best. Next, we show the key ablation study. With dark ISP and the synthesized low-light images, the model's performance is even getting worse. However, after adding our reflectance decoder, the performance is largely boosted, and we show that only using the reflectance as a learning target, the method performs the best. Next, we compare the newly introduced image decomposition process with the vanilla one by comparing their loss and their results. They show that only using our newly proposed recomposition coherent loss, the improvement is the largest. At last, we show the varied choices of the loss functions in neutral feature alignment loss. The KL divergence is the best choice as it doesn't apply a very strict constraint for the alignment between the features. In this section, we show some visualization results and their corresponding analysis. First, for well-lit and low-light images, we visualize their features and also show their statistics. We show that on real low-light images, like dark-faced images, compared with the base detector DSFD, our method DINet shows more details in the features. And for paired well-lit and low-light images from LOL V2, we show more consistent features regarding the details and for the features. And secondly, we investigate into their channel statistics and show that there are some inconsistency between the features of well-lit images and low-light images in the vanilla detector. However, after applying our method, their channels are also better aligned and more consistent. This is why they have a better generalization ability to the low-light images. And at last, we show the qualitative examples to show the improvement of our method. And here are more results on dark phase, more results on X-dark, and we show the visualization of the predicted reflectance from our decoder. In conclusion, by working in zero-shot denied domain adaptation, we achieve low-light detection without any real low-light images, therefore releasing the burdens to collect and annotate real low-light images. And detectors that learn reflectance representations could obtain illumination invariance. And we show that by proposing a stronger image decomposition process, we could also further enhance the reflectance information with the model. Thank you for listening. And if you are interested, you could scan the QR code to visit our open source resources.